ನಿನ್ನ ಫೋನ್ ಸೈಲೆಂಟ್ ಮೇಲೆ ಹಾಕ್ಬಿಡು.
ಇದನ್ನು ಸೈಲೆಂಟರ್ ಹಾಕಬೇಕು. ಬಟ್ ಐ ಶುಡ್ ವಾಚ್ ಯಾಕೆ ಗೊತ್ತಾ?
ಸೌಂಡ್
ವಿತ್ ಪ್ರಾಬ್ಲಮ್ ಆಗುತ್ತೆ.
ಸೌಂಡ್ ಆಲ್ಸೋ ವಿಲ್ ಇಂಟರ್ಫಿಯರ್.
ಅಲ್ಲಲ್ಲ, ಸೌಂಡ್ ಐ ಕ್ಯಾನ್ ಪುಟ್ ಎಟ್ 0, ಬಟ್ ಇದು ಬ್ಯಾಂಡ್ ವಿತ್ ಹೊರಟೋಗುತ್ತೆ. ಸೊ ಐ ಶುಡ್ ಸ್ವಿಚ್ ಆಫ್ ಮೈ ಲ್ಯಾಪ್ಟಾಪ್.
ಅವನಿಗೆ ಫೋನ್ ಮಾಡಿ ಕೇಳು ಯಾವಾಗ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೇಕು ಅಂತ. ಇಲ್ಲೇನು ಮೆಸೇಜ್ ಕೊಟ್ಟಿಲ್ಲ.
ಹಲೋ, ಯಾ, ಆಯನ್ Okay, we can start now. All right. All right. Yes.
Hello, good evening everybody. It's indeed a pleasure to be speaking this evening on the Think India platform of the Paschim Bengal, and I would like to thank first of all Professor Ayan Datta and then Deepak Singh and Sunil Patel for making this possible. And during this period of COVID, what I felt was that I should talk about something that will actually kind of enrich us in terms of the kind of human achievements that have taken place over many millennia. So I am talking about something that has been an extraordinary achievement of the human mind, one of the greatest I would imagine, and this has to do with the story of the atoms and the chemical sciences. So when did chemistry actually begin? Chemistry began when humans started creating and controlling fire. So when they could control fire, slowly they were able to have farming, dairy and baking and some metallurgy and some medicine and all these things. And because the food that they were eating was going to be cooked, so they could digest it easily and it did not take too much time to actually eat and so forth. And so it gave them a lot of spare time to think about various things and ponder over many things. And in fact, this kind of social evolution actually overtook everything that one could think of as genetic evolution. And so the Homo sapiens, even though they were not the strongest race, actually became one of the most dominant races. And because of the spare time that they had, they started thinking about various things, particularly about the concept of matter. So one of the early questions that was actually asked, particularly in Hindu philosophy, was, is matter infinitely divisible? That is, can you keep on dividing matter? Like if you take a stone, you break it further, and like that. Can you keep doing this infinitely? So that was one of the questions that was asked, and the earliest answer to this question was from the Hindu culture, and this was in the 6th century BC by a saint by the name of Kanada. Kanada said, no, you cannot divide matter indefinitely. The smallest size of matter that you can have is something called Anu, and you can't go beyond that. And he also gave various properties to Anu, like he said that different materials have different kinds of Anu, and you could also form a combination of two Anus to become a Dvayanu, or combination of three Anus to become a Trianu, and combination of these Anus actually gave rise to new substances. So, and they also gave all kinds of properties to these Anus of various materials. For example, they said that Anu of any sweet substance is going to be large and rounded in shape, whereas the Anu of a very sharp substance would be thin, would be much twisted, and will be angular, and so on and so forth. But that was basically an imagination. But the most important thing is that they postulated that you could not divide matter indefinitely. But what happened was, this Kanada is a very interesting person. He was a person who was involved in non-theistic philosophy, or the Vaisheshika philosophy. So he always believed in things which could actually be observed and could be felt. And so in that sense, he was not the one who believed in God, and this gave rise to Charvahak philosophy. And of course, the Hindu thought itself actually moved on in different directions. In one direction it took was that of spiritual, answering spiritual questions, and another direction that it took was, looking at astronomy, and then mathematics, like the Brahmagupta school of mathematics to begin with, and astronomy of various people, right from Aryabhatta and so forth. So that is where the Hindu history of the atoms actually came to an end. But in the Greek culture, around 5th century, Leucippus and Democritus, they said that world is made up of two things. One, the atoms, and the other, the voids. So atoms are eternal and they make up the matter, but empty space or the voids are required for actually moving the atoms around. So that was one of the theories. And then in the 5th century BC again, Empedocles actually spoke about 4 different elements which we all know now. So these 4 elements that he spoke about were earth, air, water and fire. And he said that it is a combination of these elements in different proportions is actually what is going to give you different materials. But that was before the Pythagorean school, and in the Pythagorean school, they were always fascinated by triangles and regular objects. So what they did was they associated all these elements with what are called Platonic solids. So these Platonic solids are actually solids built up of identical polygons, and at every vertex the same number of polygons meet. So these are what are called congruent vertices. And you also have another property, which is that all these are convex surfaces. So there are only 5 of them, and they are the tetrahedron, the cube, the octahedron, the icosahedron and the dodecahedron. Tetrahedron is of course made up of equilateral triangles, cube is made up of squares, and octahedron is made up of again equilateral triangles. Icosahedron is made up of again equilateral triangles, but dodecahedron is made up of pentagons, regular pentagons. And in the case of a tetrahedron, we know that at every tetrahedral corner we have got 3 triangles actually meeting, and in the case of a cube we have 3 squares meeting, and in the case of an octahedron we have 4 triangles meeting, and in an icosahedron there are 5 triangles meeting, and so on and so forth. Well, they associated fire with tetrahedron, earth with cube, air with octahedron, water with icosahedron, and then they said heaven or universe is dodecahedron. So they also said that these different materials were formed from a combination of these. So what they actually were meaning was that you can actually break up these into different triangles and recombine these triangles to form different materials. So this was the idea of the Pythagorean school, but then Aristotle rejected the concept of atoms. He said matter is continuous and the existence of voids is basically against any of the physical principles or a violation of the physical principles. And this particularly ended the discussion of atomic theory for a long time. And then there was the Middle Ages. During the Middle Ages, what happened was there was much interest in alchemy, and in the area of alchemy they were interested in basically converting base elements into gold, and they for that reason developed all kinds of furnaces and distillation apparatus and all that, and metallurgy thrived, so also medicine and a few other things, but really there was no basic understanding. And during this period, one of the things that actually came up was something called phlogiston theory. This phlogiston theory is very interesting. I will talk about it even later. One of the things about phlogiston theory is that it is trying to answer the question why materials burn. So to say that materials burn, what they actually said was materials always consist of phlogiston. And when you have this phlogiston, and when phlogiston escapes from a material, then fire is created. So for them, ash was dephlogistonated wood, and wood was ash plus phlogiston, so that it actually gave rise to fire when you burnt it. And this phlogiston theory was, it was one of those things that took hold very strongly for a very long time. And people by then actually started measuring things like, for example, measuring the weights of materials before they burning and after burning. And what they found was that after burning, the weight of the material actually increased, whereas if it was actually phlogiston theory, the weight of the material should decrease because phlogiston has to be escaping from the material. So they started giving all kinds of ad hoc explanations like phlogiston has negative weight, or it's a levitation substance, and then when it leaves the material becomes heavier and so forth. So basically the phlogiston theory was ripe for actually shooting down, because it kind of the classic example of Occam's razor, where for justifying every little thing. You are going to add newer and newer conditions, and when you add these newer and newer conditions, then it becomes completely untenable. Well, so there were some developments that took place during this period which were really great developments. For example, in the year 1660, I think, was Boyle's law. So Boyle's law was the one that proved that inverse relationship between pressure and volume. And later on, of course, Charles' law came much later, sometime in 1780. But one other experimental technique that actually came about at this time was the way of collecting gases by downward displacement of water. For example, if you conduct this reaction, then what happens is that if that reaction is giving out a gas, you can actually collect this gas in some cylinder placed over a trough full of water, and then the water in the cylinder gets displaced into the trough, and the gas occupies the volume occupied by water before. So this was one of those really great experimental techniques, and indeed when a gas was actually soluble in water, they started using other kinds of materials like mercury to displace mercury to be displaced by the gas. So these were some of the things that were there. And around this time, sometime in 1750s, one of the greatest scientists of all times, in my opinion, Anthony Laurent Lavoisier, he came into picture. So he carried out extremely careful measurements of various reactions. For example, he would collect different gases and analyze them, or he would weigh before and after both the products and the reactants, and then will know what happens to the weight loss or weight gain and so forth. And he showed that the weight was never lost or never gained, the total weight was always a constant. And he also showed that the gases that were collected were not air, so air is not really an element. Because one of the things that people talked about was that air is an element, and he showed that air is not actually an element, because the gases that were collected were different kinds of gases with different properties. Some of them would not sustain life, some of them would not sustain a fire, some of them would actually make the fire burn brighter, and so on and so forth. So he, because of his experiments, he was able to have this chemical laws of chemical combination. And his laws of chemical combination, let me come to them. So he said matter cannot be created or destroyed, and elements combine in simple proportions to form compounds. For example, he knew that the amount of hydrogen and the amount of oxygen that were actually combining to give water was something in the ratio of 1:8 or 2:16, whatever you want to call. Okay, so then he also said that if two elements A and B form a compound, say for example you have a compound like AB, and if A also forms a compound with another element which is C, let us say, and which is AC, then he said the ratio of B and C is in simple proportions. So this is the third law that he actually propounded, and example is that of water and ammonia. So if you want to find out how much of hydrogen is in water to how much of hydrogen is in ammonia, it is 24:7. You can actually work out, because nitrogen has an atomic weight of 7, oxygen has an atomic weight of nitrogen has an atomic weight of 14, oxygen has an atomic weight of 16, and so forth, and so you can actually work out. Now, after having come to these things, he also defined what are elements. He said that elements are nothing but they are the limit of chemical analysis. So because he said that elements are the limit of chemical analysis, one of the elements that one of the materials that was thought to be elements during early periods was lime. But lime could actually be broken down into calcium and the remaining thing, which is oxygen, and so lime ceased to be an element because of his definition that an element is the limit of chemical analysis. So this was one of the great things, and based on these laws of combination, Dalton for the first time proposed atomic theory. What he said was all elements are made up of atoms. Now you see that we now have a definition of elements. So elements are absolutely pure. They are all made up of only one kind of material, and so he could talk about elements being made up of atoms, and individual atoms have a mass. That was one other thing that he said. And he also said that atoms neither can be created nor can be destroyed, and atoms combine to give molecules which are basic units of compounds. So he proposed the most abundant compound of two elements A and B to be having the formula AB. For example, for him the formula for water was hydrogen and oxygen, so the formula for water was OH, and similarly the formula for nitric oxide was NO, and the formula for ammonia was NH. Now there was a problem, because according to what is called the Proud's hypothesis, all the atomic weights have to be integer multiples of the atomic weight of hydrogen. So if you take hydrogen to have an atomic weight of 1, then all others must be integers. The atomic weights must be integers. Now if you consider the case of water, which is OH, and ammonia, which is NH, and nitric oxide, which is NO, what happens is that you get you come to a conflict, mainly that if you use the atomic weight of oxygen to be 8, then the atomic weight of nitrogen turns out to be 7, because our atomic weight of oxygen is 8, because OH has 8 grams of oxygen per gram of hydrogen, whereas nitrogen, according to that, in nitric oxide will have 7 grams of nitrogen will make up 8 will combine with 8 grams of oxygen, or the atomic weight of oxygen, or the atomic weight of nitrogen will be 7. But now you look at NH3. Ammonia is actually called NH, but 3 grams of hydrogen combines with 7 grams of ammonia and 7 grams of nitrogen, and so what happens is, from this the atomic weight of nitrogen turns out to be 14/3. So you already have a conflict. That is, if you assume one kind of a calculation for the atomic weight of nitrogen, you get atomic weight of nitrogen to be 7. But we use another way of calculating the atomic weight of nitrogen using ammonia and water, then you get atomic weight of nitrogen to be 14/3. So because of these conflicts, Dalton's theory was kind of shelved for quite some time. So because Dalton said atoms cannot be created or destroyed, and atoms are indivisible, because of that you had this problem that you could not have fractional atomic masses, and fractional atomic masses were what you are getting. And around this time there was a person by Gay Lussac. By about this time we already had Charles' law. Charles' law came about in 1780. So because of Boyle's law and Charles' law, you can actually collect gases and compare the amount of gases being given by one reaction with the amount of gas given by another reaction, by actually reducing the gases volumes to the same pressure and temperature using the ideal gas laws. And so it was possible to compare the amount of gas of one substance with the amount of gas of another substance. Well, after having said this, what he found was something very interesting. He found that in any compound you have one second, Ishila. What happens is that in any compound you have if you assume that gases are forming reacting to form compounds, for example hydrogen and oxygen. So he found that 1 volume of oxygen reacted with 2 volumes of hydrogen to give you 2 volumes of water, and similarly 3 volumes of hydrogen with 1 volume of nitrogen would give you 2 volumes of ammonia, and so on and so forth. So this particular thing that the volume was going to be consistent. That is, in the sense that you had a law of chemical combination in terms of volumes. So if you took the volumes, then the volumes of the components in a particular compound was always in simple proportions. So this was the Gay-Lussac's law of combining volumes. Now it is here that Avogadro came to picture, and what Avogadro said at this point was very, very interesting. So he ignored the fact that, say for example, particles or atoms of oxygen are different from atoms of nitrogen, or atoms of hydrogen are different from molecules of different from particles of water or particles of ammonia and so forth. But he said the following, that is, equal volumes of gases under identical conditions have equal number of particles. This was one of those brilliant postulates. It was Avogadro's postulate, and based on this postulate, what he did was he went on to find out how he could revive atomic theory. So he found that one volume of oxygen was combining with 2 volumes of hydrogen to give you 2 volumes of water. So which means that in every volume of water, or in every particle of water, there is half a particle of oxygen. Now this is very, very strange at that time, because if particles are atoms, they are indivisible, and so you cannot have half a particle. But on the other hand, what Avogadro said at that time was that oxygen was actually a molecule consisting of 2 atoms, and it gets divided, and one atom gets attached to 2 hydrogen atoms, and thereby half of this particle of oxygen molecule is the one that is involved in the reaction. Now this was absolutely revolutionary, because for the first time you introduce the concept of molecules. So, and the problem of that period was the following, that is, around that time there was sometime in the 1820s and 1825, there were people like Berzelius and Sir Humphrey Davy, who actually were very much influenced by the electrical measurements or electrical ways of producing elements, because Berzelius produced many elements by electrolysis, and so they always thought that elements could be classified as electropositive or electronegative, and if you are looking at the atoms of any 2 of the same element, they have the same positivity or negativity. For example, if oxygen is electronegative, then 2 oxygen atoms of course are electronegative and negative, and they cannot combine. So if they cannot combine, they cannot form a molecule. So this was one of the major objections to Avogadro's theory, that you cannot have a diatom of the same element, because 2 atoms repel each other. And because of this, and also because of the fact that around 1811 he was in Italy, and much of the chemistry and chemical ideas were actually getting generated in France and Germany, and he was quite removed from France and Germany intellectually, so his idea was not greatly appreciated or accepted at that time. And besides, there was also another reason. The other reason was that sometime in 1828, Wohler synthesized urea, and urea, as you know, is actually an organic compound, which means a compound that is found in life. And it was up till that point, it was thought that the organic molecules could not be synthesized in the laboratory, because they are actually life-based molecules. So when Wohler synthesized urea, then it opened the floodgates, and people started working in the area of organic chemistry. And because of this interest in organic chemistry, the atomic theory was kind of put on the back burner. But in the year, then there was another scientist, very famous scientist now, by the name of Cannizaros. What Cannizzaro did was, he picked up Avogadro's theory, and he assumed that molecules do not have the same number of atoms, like for example, the molecule of water is not OH but OHX, let us say, and similarly the molecule of ammonia is NHX, and so forth. So what he did was he determined the atomic weights of various elements. For example, he looked at chlorine. In HCl, if you look at 1 atom of hydrogen, 1 gram of hydrogen combines with 35.5 grams of chlorine to give you HCl. So the atomic weight of chlorine, he said, maybe, let us assume it is 35.5. Then he went to something like calcium chloride. From there, he got the atomic weight of chlorine to be 71. And then he went to aluminum chloride, let us say. So there he got the atomic weight to be 106.5. So, and after looking at these numbers, 35.5, 71 and 106.5, he said the highest common factor is actually 35.5. So that should be the atomic weight of chlorine. So that's how he came to the conclusion that you could take atomic weights as the highest common factor of the weight with which the weight that you get from various compounds that you analyze. And this was although there was some problem with fractional weights, because it's again against the Proud's hypothesis, but we'll come to that one a little bit later. And this way Cannizzaro was able to obtain atomic weights of all the elements. In fact, one of the things is, for example, he did not find an atomic weight of 17.75 or 88.5, so which means that you cannot have atomic weight of chlorine to be 17.75, it has to be 35.5. So that way he came to the conclusion, and he came to a table of all the atomic weights. And then there was one of the landmark conferences in 1860 called the Karlsruhe Conference. And in Karlsruhe Conference, he presented his paper, and this led to the acceptance of the atomic weights of all the elements. So with the acceptance of the atomic weights of all the elements, which were actually measured not only by Cannizzaro but also by Laurent and Gerhardt, it changed the entire picture of chemistry. Now, around that time, by 1860, almost 60 elements were known, and people were trying to arrange these elements in some fashion. One of the earliest ones to do that was Dobryner in 1829. And Dobryner in 1829 tried to arrange all these elements as triads. So, for example, he would arrange, fluorine, chlorine and bromine as a triad. Okay, and similarly, for example, sodium, lithium, sodium and potassium as a triad. And he found that the atomic weight of the middle one was kind of an average of the atomic weight of the two extremal atoms in the triad. And he also found that the atomic weight increases by the same integer in going from like for example going from one element to the other element in the triad. It's actually a multiple of the same element, of the same number. For example, if something increases by 8 in going from A to B, the next one can increase by 16 or 24. So in that sense, okay. So this was one of the very early ways of actually organizing the elements in the system. Then in 1862, there was a person by name Jean Courtois, and he created what is called the telluride helix. And what he did was plot all these atomic weights on a scale of 16 on the x-axis, and on the y-axis, the atomic number was written from 0 to whatever number, the highest atomic weight that was known. And then he plotted all the elements. And then when he turned around on a helix of circumference 16, okay, then he found that elements with similar properties were lying on the same straight line, same vertical line on the helix. And this was called the telluric helix at that time. Then in 1863, there was a person by name Newlands who gave the theory of octaves. So he said that elements 1, 2, 3, 4, 5, 6, 7 will have the same properties, and then elements 8, 9, 10, 11, 12, 13, 14 will have the same properties, and so forth. And at that time, rare gases were not known, so it was not 9, but it was octaves. So 1 and 8 would have the same properties, and not 1 and 9. It should have been 1 and 9 if we had known about the existence of the rare gases. And then there was another scientist by the name of Mayer, who in the year 18 very early on, when the number of elements were very small in number, so he tried to organize them in the form of a table. And again, he did the same thing in the year 1868 and showed it to some friends, but it got published only in 1870. And so in 1869, when Mendeleev published this periodic table, it was an independent and original work by Mendeleev, although the claim is that Mayer had done this work earlier, a year earlier, but it was published a year later. And the great thing about Mendeleev was not only that he arranged elements according to a table such that elements of the same property fall in the same column, but he also found at least 11 instances where he had to interchange the position of the elements, so that by interchanging the position of the elements he could get the periodicity in the property, or the properties agreeing with the other elements in the column. For example, he had to interchange tellurium and iodine, so that iodine falls in the halogen group, which is chlorine, bromine, fluorine, chlorine, bromine and iodine. And similarly, this he had to do about in 11 places, and we'll come to a justification for this one. And later on, he also found that there were some places where it would not fall exactly into the property of the other elements in the column which were known at that time. So what he did was he created certain vacant cells within his periodic table, and these cells he predicted would be new elements. For example, he predicted things like Eka boron, which was actually scandium, and then he had gallium and germanium, or two other elements that he predicted. And in fact, he predicted 10 new elements, of which 7 elements were actually found, and 3 of them during his own lifetime. That's a great achievement. It's one of those extraordinarily intuitive things that he ever did, that humans ever did, because he was able to create a table, and from the table he was able to predict the properties of the new elements which were not discovered until then. And when they actually discovered those elements, they found that the properties of these new elements very closely matched to the predictions of Mendeleev. So that was one of the greatest things. And of course, now the periodic table is almost full, in the sense that you have elements up to element number 118. Well, one may question, what will be the highest atomic number of the element that you can ever have? One can answer that tentatively, in the sense that, if you are looking at the Bohr hydrogen atom, you see that the speed of the electron in the 1s orbit depends upon the atomic number Z. So if the atomic number Z goes to about 137, then the speed of the 1s electron in the 1s orbit exceeds that of the speed of light, which cannot be according to theory of relativity. So which means that probably the highest atomic number element that you can ever discover by whatever techniques that people have been using, like scattering heavy atom nuclei, you can probably get up to about 137 and not beyond that. Right now, the periodic table is full up to about 118 elements. Well, now what? After the periodic table, what? So, like I said, that there were the theories of Davy and Berzelius, which said that the atoms can be classified as electropositive or electronegative depending upon the electrode at which they can be collected in an electrochemical experiments. For example, if something is collected at a cathode, then the element is, let me think about it. So the element is electropositive. If it is collected at the anode, the element is electronegative. And so based on that, they said electropositive elements form compounds with the electronegative atoms, and the molecule that is formed may completely satisfy or make the system neutral, or there may be some polarity left. If some polarity is left, then it can form another, it can take on another atom. So this was generally the thinking, and of course they also assumed that two elements of the same atom could not combine simply because they will be repelling each other. Well, this particular theory of Davy and Berzelius were successful in explaining inorganic compounds. For example, they could say how sodium chloride could be formed or how calcium chloride can be formed and so on and so forth. But when it came to organic compounds, it hit a bottleneck, because the bottleneck that it hit was interesting. So supposing you look at an organic compound. In an organic compound, you can carry out a substitution reaction in which you replace the hydrogen atom by a chlorine. And we know very well that hydrogen is electropositive, but chlorine is electronegative. So the question is, if Davy's theory is right, how can you replace an electropositive element by an electronegative element in a compound? So obviously this could not be explained, and this failed. And it was around this time there was another person by name Edward Frankland. So Edward Frankland came up with the concept of valence. He said valence is the combining capacity of an atom with other atoms. For example, the valence of hydrogen is 1 because it can combine with one atom of any other substance, whereas valence of oxygen is 2 because oxygen can combine with 2 atoms of hydrogen. So valence is actually the combining capacity of an atom with the number of hydrogen atoms, or if the hydrogen atom it does not combine with, then you can have an intermediate atom and then find out the valency of that atom and then appropriately rescale the combining capacity of your given atom in the calibration scale of the hydrogen atoms. So he, based on this, he came up with the fact that you have valency of carbon which is 4, valency of oxygen is 2, valency of hydrogen is 1, and so on and so forth. And of course, we had this molecular weight could be determined by various techniques. Even those days, for example, you could use this, you can, if you are having a volatile substance, you can evaporate it and then collect the vapor, and then find out how much of the gas is evaporated to get, say, for example, how much of the liquid is evaporated to get 22.414 liters of the gas at the standard temperature and pressure, and that corresponds to 1 mole of the substance. So you would know the molecular weight of the substance. So it was easy to obtain the molecular weight of the substance, and once the molecular weight of the substance could be determined, then using atomic weights and using chemical analysis. So what happens is, if somebody gives you a compound, what you do is you do a chemical analysis, so you know the ratio in which each element is present, and then you do a molecular weight determination. So once you do the molecular weight determination, you know how much of each element is present given that they are in that particular ratio. Okay, for example, if you look at something like a system like hydrazine N2H2, okay, so you will get the chemical analysis will give you the formula as NH, but if you do a molecular weight determination, you will find the molecular weight is actually twice that of NH, which means that there should be 2 atoms of nitrogen and 2 atoms of hydrogen. So this way they could actually come to the molecular formula of the compounds. So the molecular formula of the compounds were obtained, and they had some very strange observations when they determined the molecular formula. For example, they took ethanol and determined the molecular formula. So the molecular formula of ethanol was C2H6O. And you can also take ether, and ether is also dimethyl ether. If you take the molecular formula of dimethyl ether is also C2H6O. So now you have 2 substances which have the same molecular formula but completely different properties. For example, ethanol has a boiling point of 78 degrees centigrade, whereas dimethyl ether is a gas at room temperature with a boiling point of about minus 35 degrees centigrade or somewhere close by. So given that, now the question is, how is it that you have molecules which have the same composition but have different properties? It was around this time that a scientist by the name of Cooper came up with the structural formula. He said the atoms are connected differently in ethanol compared to dimethyl ether. And this was something that was outstandingly intuitive. And so they were able to write down the structure of simple compounds like dimethyl ether or ethanol by doing chemical analysis and also chemical reactions to give different products. And so they came up with this particular concept that you can have the same molecular formula but different properties, and there are different molecules, and these different molecules were called isomers by Berzelius. So Berzelius was the first person who introduced the term isomers into chemistry. Then there was this Louis Pasteur who was studying tartrate crystals. So when he prepared these tartrate crystals, he could see under a microscope that the tartrate crystals were actually two different kinds of the same chemical compound, and these two different kinds were mirror images of each other. So they were actually, one type of crystal was a mirror image of another type of crystal, and they also had very different properties, slightly different properties, I would not say very different properties. So for example, if you made a solution of one particular type of crystal and passed plane polarized light through that, then the plane of polarization was rotated in one direction, whereas if you made a solution of crystals of the other type and passed the same plane polarized light through this particular solution, then what you would find is that in that particular case the plane polarized light would rotate the plane of polarization in the other direction. So because they were in different directions, they were actually called optical isomers, and the understanding of optical isomers was not there yet. But then in 1874 there were two scientists by the name of Van 't Hoff and Lebel, and both of them working independently came up with the idea that the four valencies of carbon were not planar. So they were not within a plane, but they were actually three-dimensional, and they said these four valencies are directed along the corners of the tetrahedron with a carbon atom at the center. And with this they were able to explain both the optical isomerism, and this was one of the landmark papers which showed that one could explain other kinds of isomerism as well. Now I have been mainly talking about the contribution of chemists to atomism. So what about physicists? Did physicists view matter differently? One of the persons who strongly believed in atomic theory was Boltzmann, and in fact Boltzmann's statistics actually depends upon assuming that the atoms or molecules are present. But very famous physicists of the time like Max Planck and Ostwald and Mark, all of these people did not agree with the existence of atoms. So they said that matter was continuous and there was nothing like atoms. But of course, Planck, when he explained his black body radiation, he had to use Boltzmann's statistics, and then it was at that time he realized that actually atoms are the matter is made up of atoms. So he got converted to atomism, but Ostwald did not readily get converted, and all this conversion happened because there was one thing still missing, and the missing thing was the determination of counting the number of molecules of a gas under standard temperature and pressure in a given volume. Okay, so this was something that was not actually achieved at that time. One of the persons who tried this was a person by name Loschmidt. It was in the year 1865. He estimated the radius of a molecule from viscosity and mean free path, which were actually known because you had the kinetic theory of gases and there was a relationship between viscosity and mean free path, and from this he could get the radius of the atom, and once getting the radius of the atom, he had to find out how much a given volume of air, or given volume of air when it is cooled, how much you would get, how much of volume you would get of the liquid air. Okay, so, and this was at a time when air was not yet liquefied. Okay, this was much before liquefaction of air. So what he did was very interesting. He took NO2, one of the gases which could be liquefied easily, and N2O, which could also be liquefied, and he assumed that air is made up of 77% nitrogen and 23% oxygen, and based on that he kind of found out what was the volume of air in, say, liquid air in, say, 22.414 liters of air at standard temperature and pressure. So he was able to obtain that, and since he also had an estimate of the volume of the radius of the particles, because he assumed all the air particles to be spherical, so he could calculate a number, and the number that he got, which is now called the Low-Schmidt number, is 4 into 10 to the power 23, which is remarkably close to what is now known. And in fact, one of the places from where this error came about was from the fact that he did not correctly estimate the size of the atoms or size of the molecules in the air. Okay. And sometime in 1909 or so, Robert Perrin estimated this from the van der Waals equation of state, because we know that in the van der Waals equation of state you have the correction term for the volume, and the correction term for the volume corresponds to the volume that is occupied when the entire gas is actually liquefied, and this volume could actually be obtained by fitting your gas isotherms to the van der Waals isotherm, the pressure temperature, the volume temperature, or the curve to the pressure volume curve to the van der Waals equation. So from this he actually got the Avogadro number to be 6.25 into 10 to the power 23, which is extremely close to what we know today. And of course Perrin also measured the Avogadro number by different techniques. One of the interesting techniques he did was he had this particles which were actually some kind of gamboge particles, okay, which are very, very small, of the order of a few microns in radius, and he created a monodispersed set of these particles by repeated centrifugal fractionation. So he did centrifugal fractionation, and he got 17,000 particles of these, which were roughly the same size. And what he did was interesting. He took a column of water which was just about 0.1 millimeter. In this column of water, he tried to measure the number density of the particles as a function of height every quarter micron at every quarter micron distance. And based on this, he got the distribution of the number of particles as a function of height of the at which they are found in this 0.1 millimeter column of water. And from this number, he did a Boltzmann distribution, which was simply that the energy here in this case is given by the potential energy mgh, and from this he got the Boltzmann constant. So once you know the Boltzmann constant, you also know the gas constant. The gas constant is nothing but Avogadro number times the Boltzmann constant. So he ratioed the gas constants to the Boltzmann constant and got the Avogadro number. There were also other ways of actually obtaining it from his experiments, because people did put a video camera, followed the Brownian motion of each one of these particles in this 0.1 millimeter column of water, and from the motion of these particles they did a computer analysis, obtained the mean square displacement of each of the particles. From the mean square displacement and the time at which the time intervals at which they actually obtained this displacement, they could get the diffusion coefficient, and the diffusion coefficient is nothing but sigma by delta t. And from the diffusion coefficient and Stokes-Einstein equation, they could always get the value of kb, because they knew the radius of the gamboge particles. Based on this, they could also get the Avogadro number. There were other ways of actually getting the Avogadro number as well. The ways by which they could get the Avogadro number, for example, was by collecting helium from the radioactive decay of radium. So radium has about 1500 years or so is the half-life, and using Geiger counter, they knew the number of particles that are being given out by the alpha decay of radium, which was like 3.4 into 10 to the power 10 particles per second. So what they did was to collect these particles. These particles pick up electrons from the atmosphere and become helium. So they collected the helium that is actually obtained from the alpha decay of radium over a period of 83 days or 132 days, and then they found out from this the number of helium atoms that were actually obtained, and because they knew the number that is obtained per second, and from this they could also know the volume of the helium atom that was there. So they could scale up the volume to 22.414 liters, and from that they could get the Avogadro number. So this was one of the ways of doing it, and Planck also estimated the Avogadro number from his distribution law. And one of the most accurate measurement of the Avogadro number is through an X-ray measurement. In X-ray measurement, you can actually get the volume of a unit cell by experiment. And if your crystal that you are studying, say for example like a crystal of silicon, is completely defect free, then you know that from the system you can actually find out what the density of the silicon atoms in the crystal is, in the unit cell is, and knowing the number of unit cells that are there in one mole atom of silicon, you can always ratio the volumes and get the Avogadro number. And the Avogadro number that was obtained in this case was 6.0221415 into 10 to the power 23, and it's one of the most accurate numbers that is known. It is known to an accuracy of better than 1 part per million. And so this was an extraordinary achievement, and once the Avogadro number was determined, then there was no more question about the existence of atoms. So 19th century was actually a century of atoms, because they postulated the existence of atoms, they established the existence of atoms, they also showed how atoms combine, and so on and so forth. And incidentally, all these things happened even before electron was discovered. Electron was discovered by J.J. Thomson in the year 1895, and even before that they knew how the bonds are formed, and the three-dimensional valence of carbon, and so on and so forth. And in fact, with the advent of quantum mechanics in 1926 and all the modern theories, the picture of bonding of molecules has not undergone any qualitative change. So it is something to be said about the imagination and the creativity of the people of the 19th century who worked on this particular problem. And of course, in the 20th century, which is called the century of the electron, you had the things like Lewis dot structure, and the definition of covalent compounds, the coordinate bonds, the covalent bonds, and the ionic bonds. And you had the Schrodinger quantum mechanics, and then you had hybridization to explain the shapes of molecules. And of course, on the experimental front, you had atomic numbers being determined by Moseley's experiments, and based on Moseley's experiments, the atomic numbers that were determined showed that the way the periodic table was arranged by Mendeleev was according to the periodicity of the atomic numbers, and the periodicity of atomic numbers could always be explained by the modern quantum mechanics. And so even without the knowledge of any modern quantum mechanics, Mendeleev was able to arrange his elements such that the tables, the groups or the columns actually belong to either something like the S group column or the P group column or the D group column, and so on and so forth. And and then of course you had the Aston mass spectrograph, and Aston mass spectrograph was the one that showed the presence of isotopes. Isotopes are those which have the same atomic number but different number of neutrons, which means that they have different atomic weights. And depending upon the abundance of different isotopes, you will have different fractional atomic weights of a mixture that is naturally found in nature. And so, for example, the atomic number of chlorine being 35.5 could be understood because atomic number 35 and 36 of, rather not atomic number, the mass number 35 and 36 of chlorine atoms were present almost in equal proportions. Well, with this, I come to an end of the story of the atoms, because I am not going to go into the century of the electron and the new techniques that were developed and where chemistry is going and what is the future of chemistry and so on and so forth. But I would like to read out a quote from Feynman, which is one of the very interesting quotes that he gave, and which is a great tribute to the ingenuity and inventive way of thinking of the people of the 19th century. He said, "If all scientific knowledge were lost in a cataclysm, what single statement would preserve the most information for the next generation of creatures? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world, if just a little imagination and thinking are applied." So this is a quote by Feynman, and with this I will end my talk, and thank you very much for actually listening to it. Bye. I will take any questions if you have. Hello. ಅವನು ಫೋನ್ ಮಾಡು.
Hello. Any questions? It's okay, so we close it now? Okay. All right, thanks. Bye.